I've got a real treat for you today. Something that is a tricky problem that some of you were asking for more examples of. I came up with one that's a little bit nastier than the one that I asked you about on a test, but follow this through and let me know if you have any questions. So what we're going to do here is we're going to actually consider integrals that look like this, where you have the integral from 0 to pi over 4 of the nth power of secant. Okay, and just as a reminder, secant is the reciprocal of cosine. It's not inverse cosine. Some of you got that mixed up, but it's the reciprocal of cosine. So our functions look like this, for example. There's secant of x. There's secant squared x. There's secant, oops, not that. Oops, secant to the third power of x. Is it not going to do that? Ah, okay, use parentheses. So here's secant to the third power, and et cetera, et cetera. In fact, I could ask it to do secant of x raised to the n, and I can add a slider for n, and you can look at what happens as we raise it to different powers. I think I can change this to go from 0, let's go to 10, and let's have a step value of 1. Then we can see really what it looks like for the first 10 iterations. So that's what we're going to be integrating. And on all of those, we're going to be integrating them from x equals 0 to x equals pi over 4. So I can even zoom in on just that interval right there. We're going to be finding that area under the curve. Okay, wonderful. So let's use Desmos 2 to check our answers as we go through this process. So I'm going to clear out everything for now. What I'm going to do first is figure out when n is equal to 0. All right, so 0 to pi over 4, secant to the 0. Well, secant to the 0 is equal to 1. Anything to the 0 power is equal to 1, even if it's a function. So 1 dx becomes the integral of just x from 0 to pi over 4, which is just pi over 4. Okay? And so if I went through here and then I copied this answer down and I asked to do the integral from 0, oops, come on, there we go, to pi over 4 of that dx. It tells me it's 0.884. That's when n is equal to 1. So when n is equal to 0, I should get 0.785. Let's double check. Same answer as before. So that's great. Now we know I0. Let's do I1. I1 integral from 0 to pi over 4 secant x dx. This is a tricky one. The way you find this integral is you actually write it as a fraction, but maybe not in the way that you would expect. You write it as secant of x times secant of x plus tan x. You can't just multiply the top, so you also multiply the bottom. So I'm really just multiplying by a fancy version of 1. And the reason that I do that is pretty clever. If you distribute out the numerator, you get secant squared x plus secant x tan x. And if you just write the bottom down again, what's really nice is the derivative, come on, work with me, the derivative of tangent is secant squared, and the derivative of secant is secant x tangent x. So that suggests that if I do a u substitution for the bottom, then my du is the top, plus secant squared x dx. So my original integral becomes 1 over u du. And so we have the natural log of the absolute value of secant x plus tangent x. And that's evaluated from 0 to pi over 4. I told you I had a real treat for you today. Okay? You asked for something like this. When you do secant of pi over 4, you got to think about cosine of pi over 4. Cosine of pi over 4 is square root of 2 over 2. So secant is the reciprocal of that, 2 over square root of 2, which is the same as just square root of 2. And tangent is 1. Then when I plug in 0, secant is 1, and tangent is 0. So I just have the natural log of 1, which is 0. So this answer right here is the value of the integral of secant. Let's just double check our answer. So I'm going to slide n equal 0 to make it n equal 1. 0.88137, blah, 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 blah. Let's see if we got it right. Natural log of square root of 2 plus 1. Check it out. It works. Exactly the same answer. You can see it right there in the function zone. Okay. Next, I'm going to do secant squared. I'm going to clear out my screen because I have my two answers here. That pi over 4 was the answer for I sub 0, and this nasty natural log thing is the answer for I sub 1. So let's clear. And just a second. All right, so what I was saying is that we are going to do the second power now. So I2 would be the integral from pi over 4 of secant squared x dx. Surprisingly, this is much easier than the previous integral because secant squared is the derivative of tangent. So I just go tan x from 0 to pi over 4. Tan of pi over 4 is 1. Tan of 0 is 0, so just becomes 1. And what's kind of interesting is the formula that I'm going to come up with in a second that relates these together, because it's totally not obvious. Obviously, we know what 1 equals. I don't even know why I typed 1 into the bar, maybe just to save my answer for later. And check it out. When I put n equals 2, I get an answer of 1. So we have these three answers here that seem completely unrelated to each other. My claim is that they are actually related by an integral reduction formula. And so let's consider now the general case of the nth power of secant. And I thought about a couple different ways that I could approach this. My thought was integration by parts. And my thought was that if I can leave a secant squared in the integral, then I know how to take the antiderivative of it. So when I'm doing integration by parts, I'm going to choose u equals secant to the n minus 2 power, and then I'm going to try to integrate it. Just give me one sec. All right, so again, I'm choosing that. The reason I'm choosing that for my u is because then dv is something that I can integrate, secant squared x dx. And so then if I calculate du, you multiply the power in front, you write the inside function again, minus 1 from the power, and then you multiply by the derivative of secant, because that's the inside function. So that whole nasty thing is du, and v is just tangent of x. And this works out very nicely. When I set up my u, v, I get secant of n minus 2x times tangent of x, that's uv, and that's going to be evaluated from 0 to pi over 4, minus the integral of v times du. So I'm going to copy and paste all that junk in there. N minus 2 secant. I can combine these to make n minus 2 tan x dx. So double check, look back over that, maybe pause the video. Do you see where all of those pieces came from? I had a u, a v, a v, du. Okay? Now we're going to do some plugging in and some simplifying. If I plug in pi over 4, I told you earlier that secant is the reciprocal of cosine. So instead of square root of 2 over 2, it's 2 divided by the square root of 2. 2 divided by the square root of 2 is the same as just the square root of 2. You can see that that's true if you multiply both sides by square root of 2. So when I plug in pi over 4, I have square root of 2 raised to the n minus 2 power. Tangent of pi over 4 is 1. And tangent of 0 is 0. So that's all that happens for the first piece. The second piece, I can bring an n minus 2 in front, and I have 0 to pi over 4. And I have tangent times tangent, so I'm going to write that as tan squared x secant to the n minus 2 dx. I'm going to recall a trig identity, so I'll kind of do this over here in the top left corner of the screen. We remember that sine squared x plus cosine squared x is 1, but we want something that talks about tangent and secant. Tangent and secant both have cosine in the denominator. I'm going to divide my original Pythagorean identity by cosine squared. Sine over cosine is tangent. Cosine over cosine is 1. 1 over cosine is secant. So I get this identity here, and I'm going to substitute that in for tangent of x. So tangent of x will be secant squared minus 1. And remember that this is all equal to my original nth integral. So now we're doing a little simplification. We have square root of 2 to the n minus 2 times 1, so I don't need to write it down, minus n minus 2, 0 to pi over 4. Tangent is replaced with secant squared minus 1. And I hope you can see how this is going to work out. If I distribute that, that becomes secant to the nth. If I distribute that, that becomes secant to the n minus 2. So I can write this. Square root of 2 to the n minus 2 minus n minus 2 copies of, when I distributed the secant squared, I got secant to the nth, and that's the I sub n. When I distributed the negative 1, I got secant to the n minus 2, and that's I sub n minus 2. So now we're just doing some algebra, just solving for x in terms of y. So I sub n, square root of 2 to the n minus 2, minus n minus 2 copies of I sub n, plus n minus 2 copies of I sub n minus 2. So I'm going to create just a little bit of space up near the top to write my final integral reduction formula. And then I'll show you how you can get, recursively, you can get any power of secant without doing any more calculus, which is kind of nice. Okay, almost done. Okay, I'm going to switch colors just so it's clear what the new stuff is. What I'm going to do is I'm going to add n minus 2 copies of I sub n to both sides. So if I have one copy and I add n minus 2 copies, 1 plus n minus 2 is n minus 1. So I have n minus 1 copies of the integral I care about, and that's equal to square root of 2 to the n minus 2 plus n minus 2 I sub n minus 2. So the last step is to solve. So you divide everything by n minus 1. So I sub n equals square root of 2 to the n minus 2 plus n minus 2 I sub n minus 2 all divided by n minus 1. Great. So let's check if that is a true statement. So we have 3 answers so far. We have 1 and this natural log here and pi over 4. So what I'm going to check is, does 1 equal pi over 4 inserted into this formula? So let's erase a little bit more. I wish there was an easier way to erase more, but okay. Okay, so let's try it. According to our formula here, I2 is going to be square root of 2 to the 2 minus 2 plus 2 minus 2 I0 over 2 minus 1. Oops, I wrote 2 parentheses. I meant 2 minus 1. And that ends up being, this is 0. This is a power of 0. This is 1. That equals 1 over 1. So it does work out there. But the cooler thing is that you can predict a future answer here. So I'll type it in to the bar on the side here, that I think that the third power is going to be the square root of 2 raised to the 3 minus 2, which is just 1, plus 3 minus 2, which is just 1, times the integral I got for I sub 1, so that's this answer here, all divided by 3 minus 1. Let's check our answer. 1.1477, make n equal 3. It matches up perfectly. I predict also that if I wanted to do the secant to the fourth power, I can do a very similar thing. Square root of 2. Now it's raised to the second power, because that's 4 minus 2, plus 2, because that's 4 minus 2, times the integral from 2 steps below, divided by 4 minus 1. So I should get 1.3. Let's check our answer. Slide n equals 3 up to n equals 4. Check our answer. And it matches up perfectly. So there you go. You asked for another example of integration with a reduction formula and with trig, and I came up with this example for you. So ask and you shall receive. Let me know if you have any questions. Happy to explain more.